Assalamualaikum. My name is Sandar Dipaja. I'm an assistant professor at Faculty of Engineering and Technology, University of St. John's. So today we are going to attend an online lecture for one of my subjects, Computer Vision and Image Processing, which I teach to BS Electronics Part 4 and BS IT Part 4 accordingly. As you know that we are going through a pandemic situation, so the HEC and university has announced that we are moving towards online education system. So this is my first video in which I am going to deliver the lecture online through a video, and so this is my first attempt. So please let me know if there is any problem faced by any of my students, and also please do not worry about the mode of language, because I understand that many of the students cannot understand the lectures in English. I'll try to speak in English quite slowly, so it will be easy to grasp. But if there is any problem, then there will be a live Q&A session, and the students can let me know the slide number. So I'll try to explain each of the slide or the corresponding slides in native language. So do not worry about that. And I'll try to be as simple as possible, and I'll also perform some annotations in my presentation. So I think it would be easy to understand. Guys, even if there is any problem, we can sort it out in our live Q&A session. So let's get started with our lecture. Let's have a quick recap. Last time in our lecture, we discussed about Kenny's detector and Hopf transform. So Kenny's detector is basically an optimal age detector, which is helpful in detecting ages, like where the gradients occur in the intensity levels. So we have already discussed about the whole algorithm, that how we do that, how we perform magnitude gradients, how we perform non-maximum suppression, how we perform the hysteresis thresholding to detect the true ages and to ignore the false ages. Now, another thing which we learned was Hopf transform, that how we can detect the boundaries and lines by using ages as a kind of building block, and stack the Hopf transform algorithm on top of it to detect the peaks where there is most of the intersection in the accumulated array. So we have already discussed about it. Now we are moving towards corners, and some of the concepts from those of transform and Kenny's detector will play a role in this lecture. So please recap that particular slides. I have already uploaded in my learning management system, so you can easily find those lectures. And if there is any problem in downloading those lectures, please let me know. And of course, I have created a Google Classroom. So please refer to that Google Classroom for more stuff like supplementary materials, or let's say this video link and all that stuff. So you have to join the Google Classroom. And the Google Classroom ID is also uploaded in my LMS. So corners. Now we have already discussed about gradients, right? So the gradients are, let me just so it will be easy. So if we go in this direction, see, there is a gradient. The gradient is that when we enter the gray from gray to blue and from blue to gray, so there will be a gradient, and there is a shift in intensity changes. So this is in one direction only. So we cannot say that this is a coordinate. But if we have a gradient in both the directions, let's say we have the gradient in this direction, we have the gradient in this direction. Still, it's in this direction, but at this point, basically, we have the gradient in not both, but all the directions, I guess. So that's that is what we consider as corner. So it's a kind of a junction of two edges, and corners can be used for multiple applications such as uh, motion tracking or image stitching, 2D mosaics, stereo vision, image representation. It's quite helpful in implementing all those applications. But why they are helpful? Because they are considered as interest point. They are kind of a unique texture or unique patterns which are easily to match and track. And of course, they are invariant to translation. Now, what I mean by translation is that if we move this particular image or this particular corner specifically to the right or to its left, unless and until the corner gets right, it is still like the most unique point in this whole image. So it's a kind of a invariant to translation unless and until it is visible in that particular frame or in that image. And for rotation, if you just rotate it at 90 degrees or 45 degrees or just rotate it horizontally or vertically, the corner will still be the same patch, or it will still be distinctive at the same degree as it was previously. So of course it is rotation invariant as well. And illumination, I will explain you the illumination effect in the next slide. So where we have a kind of subsequent frames if we deal with videos. So there are series of frames. So in one frame maybe there is bright light, and in the next frame there could be a shift in illumination. So the corners are actually illumination invariant again unless and until they are visible. So if they are visible, they can be easily detected, they can be easily matched. So in this case, you can see that the left side is a kind of a bright and the right side is kind of having a dark intensity levels. So still the corners are detected. The same corners are detected as they are detected on the left side of the image. So this is what I call illumination gradient, that if there is a change or a shift in lighting, still the corners can be detected quite effectively. Now, in this case, if you can see, let's say that the left side is the starting frame and the right side is a kind of a subsequent frame when you move your camera to the right. So the view changes. There is a viewpoint change in the images from the left to the right. So it's like motion capture, but while you are moving your camera to the right side. But in this case, you will see that these corners, this one or this one, these corners, they are exactly the same and the patch can be matched easily. But if you consider this patch, of course, you can get it here, you can get it here, you can get it here, or you can get it here. So the problem is that these patches are not so distinctive. And if they are not so distinctive, then there will be many false positives. What I mean by false positives is that we have already discussed in age detection lecture that there are many false ages. And we do not need that, because if we get the false ages, there will be many responses. And to deal with many responses, it's like dealing with noise plus the data, and we do not need the noise. So this is one of the examples where we can see that how the corners are more distinctive and the normal intensity level patches, and we'll like discuss in this lecture that how to select a patch, how to select a distinct patch, how to visualize the distinct patch based on their intensity levels so that we can select them and we can use them for matching them. Uh, it can be used as patch matching, as I already told in the last slide. So if you can see, there is a red patch on the left side of the image, and in the right side of the image there are many patches, and these patches can be referred to as windows, right? So what we have to do is we have to find the most similar patch in the second image, which with respect to the right patch. And if you can just compare it, you will see that this one here will be selected as the most similar patch, and that's what our target is when we are making a patch or when we are making some kind of features in moving frame. But not all pages are created equal. That's one of the problems. That the patch may vary, or the patch have different, what we say is characteristics. So in this case, we have selected this red patch, and the intuition is that this is a good patch because it's a kind of a distinctive feature. Now let's say if I select this patch, how many of these patches can be matched to this image? This, 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 not this, 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 and you have this. So these are all patches which can be matched from this image. Similarly, if you select this one, that's it. So how many of them can be selected here? See, there are many patches which can be selected. So there will be multiple responses. So in this case, the patch would not be good. But if we consider this patch, which is already selected, this is a distinctive patch. And there is no other distinctive point in this image which occurs like twice or which occurs multiple times. So there will be a single response, and that's what we want. A single response to get the things matched easy or to get the things correct. So this is a good patch. But if you consider this patch, of course there will be multiple responses as I explained earlier in my previous slide. So this is not a good patch, and there would be many false responses as well. There will be multiple responses, and we do not need that because in an image, if you get multiple responses, you have to deal with a lot of processing. So the computational complexity increases, memory complexity increases, and there are other steps as well. So we actually try to avoid these false responses as much as we can, and we will see that when we perform kind of event. So the idea is to select the most distinctive patch, which is easy to track and which is easy to match. And that's where corner arises. So when you deal with corners, the corners have the most distinctive patch because they have the image gradients in all directions rather than only in one direction. And we'll discuss that when we'll like talk about one of the old techniques in the corner detection. So we'll see that what are some limitations to considering the gradient in one direction. So these corners are actually the most distinctive, as of course they have the most distinct patterns, and they are easy to track and they are easy to handle. So they are generally more stable features over changes of viewpoint, because if your viewpoint changes, like the image gets rotated or the image gets translated or there is a problem or there is a shift in illumination, you can still track those corners. That's why we consider them as stable features. So intuitively, there are large variations in the neighborhood of point in all directions due to the gradients of the corners. So simply we consider these large variations as good features because they occur rarely. They occur rarely in that particular image. They are not common when you move the sliding window from left to right, and top to bottom. So there will be some distinctness in those corners rather than those patches which are homogeneous in the particular region. Now, what we call homogeneous is that if I select this, of course, the intensity levels are quite homogeneous. There is no change. So, if there is no change, then there will be many responses. There will be many responses to this patch. And when we consider all those responses, it will be very difficult to track because if there is an image similar to this, there will be many same homogeneous, like it's a sky, right? So if there is any image with a similar sky intensity levels, so it will say that okay, this image is very similar to that image, and we do not want that. We want to match the particular image with the same characteristics. And if the same characteristics are reflected by these homogeneous regions, then there would be many false positives. By saying false positives, it's like um, you have a kind of a brown fur in cat, and you have a brown fur in some dogs. And if you consider that using that particular patch of intensities where the same color fur is matched from one cat image to another dog image, it will say that these both images are the same, but they are not. So these are the false positives. So we do not need. So the basic idea is that we should recognize the point by looking at intensity values within a small window. Now a small window is created, a patch, a kind of this. Yeah, this is a patch. This is a patch. So this patch is actually created, and this patch is kept here, like small window patch, and this will scan the image from left to right and top to bottom. So once this patch is here, kept here, let me change the color of my font. So if when this window occurs at this position, it will say that okay, this patch exactly matches what I am looking for because this is a distinctive point and you cannot find the same point uh, anywhere. So this patch actually tells that this is what I'm looking for and it will match exactly at this point. Maybe it can match this point, but it's okay because we are looking at this page and we want this information to be matched. So both of them are okay. Two responses, no problem. And similarly, this one, two responses, no problem. But there is no other similar patch which explains the system. If you want to suggest that this is the similar patch, no, because the intensity values here and the intensity values here are quite different. So we cannot select this patch or it will not match this patch to this patch. So they are unique, they have a large variations. I think I have made my point up till now that why farmers are a good way to match or a good way to obtain the distinctive feature. So as I already told in the homogeneous section, like this section or this section, so they have a flat region like here. This is this is the flat region. There is no change in the all in any direction. So they are homogeneous region. The edges, so it's like if you move towards this direction, there is an edge. If you move towards this direction, there is an edge. if you move towards this direction, there is an edge. So edge are kind of unidirectional braking changes. So there is only change in one direction. There is no change in this direction, or there is no change in this direction, or there is no change in this direction. So basically, there is no edge here. But as you move towards this direction, there is no change. This direction, there is a change. Okay. For the corners, the change is in all the directions. So that's what we call a corner, because there is a significant change, there is a significant shift in the gradients in all the directions. So let's say we want to track a patch from image I0 to image I1. So this is image I0, this is image I1, and as you can see that this I1 image is a kind of a translated version of I0. It's like the camera has been moved downwards. So the camera has been moved downwards, and you will get this result. So this is just a translated version or a shifted version. Or in this case, we will refer to it as a displaced version. So we'll assume that the intensities won't change and only translation motion. Now, translation motion and displacement motion is all the same. So we expect that the intensities, xi values, have some displacement in image I1 with respect to the intensity values in image I1. So in practice, we'll have noise, so of course they won't be exactly equal. So we will try to explain that how we can actually reduce the noise and perform the same kind of operation. So what we can do is we can search for the displacement that is in the x direction and y direction that actually minimizes this sum of squared differences. Now, why we say sum of squared differences? Because we calculate the difference from the intensity values of this. So this we calculate the differences of the displaced intensity values from image I0 to image I1, and we square them. So and we sum all the squared residuals. So it's kind of a sum of the squared differences. These weights, these are optional ones. It can be constant values, it can be random values, or this can be used as a window, as I already explained, that how the window actually moves from left to right and top to bottom. So you can consider this as the window of intensity values for averaging or for enhancing the sharpness or contrast. So it depends on the application which you are using, but this is optional. Now, as you may recall, I already told you that how to select a distinct patch. Here, selecting a distinct patch is very important in this case. So we need to consider the stability of the patch, that how stable the patch is before applying a matching problem from one image to another image. We have to first consider that which of the patch is most stable. So in this case, what we can do is we can check the stability of some of the square differences. And by doing so, we will not be considering the patch from one image to another image, but we will consider the patch from the same image. Like if we select a patch, how stable is the patch in the same image? So if it is distinct, we will not find the same patch in the same image twice or like many times. So there will be no multiple responses or many responses if the patch is distinct. So we would like to have the SSD score. You have a distinct minimum at a right value of u, and there will be an uncertainty in the value of u if there is no stability. So featureless patch will not be able to match uniquely, and This is the same thing which I explained with the homogeneous regions. That if the regions are homogeneous, let's say in this case, if you select this patch, this is a featureless patch because you will find any references here, right? False response. Here too. So you cannot match it accurately because there are many similar regions. So we want to choose the patches that are stable to break, and we can predict how stable a patch will be by comparing its SSD score with itself in the image at various displacements. So we displace a particular point, the intensity values, and then we see that how stable the patch is. And how we can do that? Remember, we use this difference, the squared differences, sum of squared differences, but in this case, let me change the color. So here it was I1, and we were like computing the differences between two images. But here we will compare the differences within this image, which is I0 and I1. Okay. So what we are going to do is we are going to displace the intensity values in I0, and we are going to check out the differences for the displaced intensity values with the original ones, and we'll see that how much error we can get. So if the surface EU has a distinct minimum, then it's a good feature to have. And what I mean by distinct minimum is, let's say, consider this patch, this blue patch. Now it's a kind of a homogeneous region, right? So there is no change or there is no gradients, apparent gradients in this image. See, all these regions are quite similar to me. There is no distinct pattern to it. And there are many peaks. So if there are many peaks, how would you select a distinct pattern on this? So the problem is that there is no apparent gradients for this patch. It's not stable. Now for this patch here, this is the response. So you will see that the gradient is quite apparent in this direction, but in this direction it's the same, more or less the same. So you will see that there is a flat region here because of these flat gradient. But there are some responses. So of course we can consider it, but we should look for more distinct patterns. Now here the red patch, the yellow patch, it's quite a good patch because there is a unique pattern to it. And if we consider these unique patterns, see, these are gradients in all the directions. So, and there is a good unique point, a good unique peak here. So basically, this is a good distinctive patch to consider rather than the red one and the blue. So what we can do is we can estimate the stability of the SSD score by taking the Taylor series. Now, in the Taylor series, what we do is we first take the function of the intensity values and then their differentiation between along with the subtraction. Now, as you move forward, you can have higher order derivatives, but we will just flip it here. So we do not want the higher order derivative, we just need the first order derivative. So the vectors x and u, we want the displaced intensity values for I0. So what we can do is we can take the derivative for it as we do in ages. So once we do, because ages also consider the gradients and gradients are referred to as the differentiation. So this term is the same as this term. You can relate to it. This sign is a kind of gradient. So we compute the gradients for I0, the intensity levels in the image I0 with respect to the displaced value. So this displaced value refers to this, and this gradient term refers to this. So you can see, and know that we are actually clipping it, right? So it's not exactly this. This is an approximation. So that's why we change the equal sign to the approximation. So once we have this, recall that our formula was this: I naught xi plus delta u minus I naught xi. And now we have computed the value for this using Taylor series extension. This one, right? So what we can do is we can replace this value by this. So I naught xi plus delta u will be replaced by I naught xi plus gradient of I naught xi values with respect to the displacement in x and y direction minus this term will remain same. So this term and this term are the same and they have opposite signs, so they will be cancelled out, and what we get is only this, which is the gradient values of the grid at image at xi, and the displacement in the form of delta x and delta y, like the displacement in x direction and the displacement in y direction. So if we expand this, what we get is the gradient in x direction and the gradient in y direction. So it's a kind of a partial differentiation. Because we are using gradient, so we are replacing it with differentiation. Now note that delta u has two terms. One is delta x and delta y. So if you differentiate it with respect to x, then delta y term will be considered as constant and it will get 0 because the differentiation of the constant value is actually 0. And when you perform the differentiation in y direction, then the delta x term gets constant and it gets 0 out. So we get these two terms, delta x and delta y, with respect to the x direction gradient and y direction gradient. Now, of course, we can apply the simple a square plus 2ab plus b square extension to it, because it's a plus b square. So this is the a term here. This is the b term. A term is delta x square, this one and this one, but this is not a kind of scalar value. These are the vector values, so we cannot just put the square to it as it is. So the delta x is the vectors, and you can see that the derivative, the partial differentiation converts to x squared. Now this 2ab means that we have to perform the gradient in x direction as well as in y direction, and the displacement in both the directions as well. And for this, again, this is the same as this square. So this is the b square. Now there is a summation sign here, and these summation sign consider the values xi. There is an xi, there is an xi, there is an xi, and there is an xi. So you can notice that there is no xi term in delta x's and delta y's. So what we can do is we can take out these delta terms outside of the summation sign. So here we take out the delta x term outside of the summation sign, and we can take this. Similarly, the delta x terms are outside of the summation sign, and yeah, that's it. So once we do that, we can represent it in a simple form, which is delta x w, which is the weight multiplied by the gradient in x direction and the gradient in both the directions. And so see this term, this is the aesthetic term, refers to the convolution. And what I mean by convolution is, let me give you an example. So let's say we have a big image here. Let's say this is maybe have some intensity values. Now what we can do is we can define a kind of window. Let's say the right window. So we have this 3 by 3 window. Now what I mean by unrolling is that we can put this window here, the 3 by 3 window, and we can move from left to right and top to bottom. So this window will be unrolled with the original image, and what we get is this response. So if we convert this window into on the gradient map, which is looking to performing the gradient in x direction, we will get this. If we perform it on the gradient map, we perform the gradient in both the directions, so we get this and this. And similarly, if we perform the convolution on the gradient map performed in the y direction, then we get this. So the SSD score is a kind of delta x, delta y, this matrix, and delta x, delta y. This is the same here. Now recall that the delta x, delta y is delta u. So we can just replace the delta x, delta y value with delta u's, and we consider this matrix as variable a. We assign this matrix to variable a. So we can write this in this one. Delta u transpose a and value where a is this matrix. So W can be an averaging filter, as I already explained. That W can be a contrast enhancement filter, W can be a sharpness enhancement filter, W can be an averaging filter. So A here is the responsible for telling us that how stable the pH is, because if the SSD score is good for this matrix, then of course the batch is good. If SSD score is not good, then the batch is not good. So the aim of this is to get higher values for each of the gradient maps. To get the higher values, you get a distinct response, and it's a kind of what to say is bad patch, because it's a homogeneous region. So consider this. You will see the gradient in y direction. So there is a change in y direction, and it can be represented by this. Here. So you will get the gradient in the y direction, the response in the y direction, and all the responses, all the other responses are zero. This is the A matrix, right? The response of the A matrix, there is only the response in the y direction. Similarly, there is only the response in x direction, which is represented here. Now, for this corner, you will see that you are getting a good response from all the directions, and there is a quite good pattern here, because there is one local minimum, and based on this local minimum, we can say that this is a kind of distinctive feature or branch that we are looking for. Similarly, if you have a kind of a step edge, so there will be gradient in all the directions, and it is occurring from the So this particular E value which we are looking for is the second order polynomial. It's in this one case is called the pH of the COS star. So it's second order polynomial. So if the value of A here, this value of A or the gradient in the x direction gets bigger, this plot gets steeper and we get a good local minimum, and that's what we want. Similarly for the C, that's what we want. So a large value of A means that E curves up sharply as x varies. So similarly, large C means that E curves up sharply as y varies. So both A and C large mean that we have a good minimum in E. So we want these two values to be bigger. Problem is that if B is not 0, B is not 0 or not near to 0, this becomes flat. So finding a local minimum gets a little bit tricky. So what we want to do is we want to make these B's as close to 0 as possible. So how can we estimate the stability here? So recall we have a similar pattern here which is related to eigenvalues. So in eigenvalues we have this format, right? That matrix A multiplied by eigenvector is equal to the eigenvalues multiplied by eigenvector. So lambda are the eigenvalues and B is the eigenvector. And we can write it in this form, where A is the matrix and B is a unidirectional vector. Values of the matrix and B is the unidirectional vector. And these eigenvalues are somewhat is explaining the variances in the image, and they are like mentioned in the descending order. So the higher the eigenvalue, it will be at the top, and lower the eigenvalue, it will be at the bottom. And this can be also represented as AR equals to this one. This is basically a diagonal matrix whose elements are the eigenvalues of A. Something like so this is the kind of matrix which is now remember that these eigenvectors are normalized into unit vectors, and eigenvectors are also orthogonal. Orthogonal means that the dot product of two vectors is equal to 0. So if these are if we compute the dot product of two vectors, then it will resemble 0. That's what we mean by orthogonal. So now R is, which is a vector v1 and v2, is an orthonormal matrix. And orthonormal means that a set of vectors is said to be orthonormal if they are all normal, and each pair of the vectors in the set is orthonormal. So if you have a kind of a matrix here, let's say A1, A1, B, B1, B1, so if we decompose them, we get these vectors. Similarly, we have A13, A23, and so if we multiply with the subsequent vectors, they should be orthogonal. And they are all normal to each other, so that's why we call them orthonormal. So in this case, this is the property which we are getting. The R transpose is equal to R minus 1. Now see, we have AR equal to this R. Now if you send this R this side, then what we get is this R will result in R inverse A equals to the eigenvalues. Now by this property, the R inverse is the R transpose. So we can write it as R transpose to R. So this is what we are getting. The columns of R are the eigenvectors of A, and this is a kind of a diagonal matrix whose elements are the eigenvalues of this. Now consider R is, let's say, a rotation matrix, and if we rotate the coordinate system, delta U equals to R delta V. So then E will become delta U. This is what we got right last time. E is delta U transpose to delta U. Now if we consider R as a rotation matrix means that you have a kind of a vector and a rotation matrix. R is a matrix, right? This rotation matrix is kind of simply, we have already discussed it. So cos theta minus sin theta 0 sin theta cos theta 0. So this is an example of a rotation matrix. And here we have already discussed that R is an orthonormal matrix, not a vector. So let's consider that this R is a rotation matrix, and it will be applied to V1, V2, V3 depending on if it's a two-dimensional or three-dimensional. So if you are considering the two-dimensional, this would be cos theta minus sin theta and sin theta, and it will be applied to V1 and V2. So this is 2D, this is 3D. So if we consider R as a rotation matrix and we apply it on the displacement values V1 and V2, then E equals to this we have already derived. So replacing the value of delta U, which is this, into this, what we get is delta V transpose R transpose A R delta V. And remember, R transpose A R is equal to the eigenvalues. See this, R transpose A R is equal to eigenvalue from this previous slide. So just replacing this value here, we get delta V transpose eigenvalues in delta V, which has the form lambda 1 V1 square plus lambda 2 V2 square, because eigenvalue matrix is something like lambda 1 0 and 0 lambda 2. So it's a kind of a diagonal matrix. So only if you multiply it, let's say with V1, so if you multiply it with V1 and V2, what do you get? So lambda 1 plus V1. Now we have to apply this class. So lambda 1 V1 plus lambda 2 V2. Here we have V transpose multiplied by V, so it will be V square. So if you just replace it with square terms like this, so you can just write V square. So it's just the multiplication of the matrix and the vector. So if both eigenvalues are large, we have a good minimum that there is no global component, no diagonal component here. But if one of the eigenvalue is low, the surface is flat along one direction. So if you have similar situation like here, that if one of the eigenvalues is low or one of the eigenvalues is low, you will get this kind of response. So it can be noted from this that if you look at the smallest eigenvalue, if it is sufficiently large, then we have a good candidate point, which was C. Here, let me explain you one thing, that what we want is that these diagonal values should be zero. That's why we are considering the eigenvalues. Now, once we get the eigenvalues, these 2 points, if they are zero, then we will just get this kind of response. And this kind of response is what we want from. That's why we are representing this coordinating eigenvalues and eigenvectors. So this is if you have a kind of a smallest eigenvalue and still if it is large, then we have a good candidate point, which is represented by C comma C here. Alternative measures that don't require square roots is Harris detector. So the determinant of A is let's say that if you have again A1 A12 A13 similar to A13 A B1 A B2 and A2. So you have this kind of net. So how can you calculate the determinant is A11 and A22 and A22 and A23 minus A12 and where you will get A21 and A31 and there it is A12 plus this will be so this is a kind of determinant. If you consider it as a matrix, and the trace is the diagonal values. So the diagonal values, the sum of the diagonal values is the trace. So if we consider the determinant of A minus the square of the trace values, which can be represented by this, when you consider the eigenvalues, then you can perform this operation, and it is referred to as Harris coordinates. Harris coordinates. And if you use this division, which is determinant of A divided by the trace of A, it is considered to be harmonic mean. And the performance of the harmonic mean and Harris is shown here. So you can see that the lambda 1 value is higher, and as you decrease the value of lambda 1 and as the lambda naught value increases and as you decrease the value of lambda naught and lambda 1 value increases. So it's like we want both the values to be high. If we want the values to be high. So this is one of the possible interest parameters, and that has been they have been proposed since 1994 and 1995. So this is one of the example of MATLAB plot. So what we are going to do here, we have to find the corner points. So first we will read the image, and we apply a kind of a Gaussian interval by applying the standard deviation, and this is a special command in MATLAB which is IM filter. So we can just apply a kind of what to say is blurring or averaging filter in the window rather onto the image, and then we'll see what the image looks like. Then we'll perform the gradient in x direction and the gradient in y direction. So see what we are going to do here, we want to replicate the same thing as here. So we want to perform the gradient in x direction in both and in y direction. So first, what we are going to do is we want to perform the gradient in x direction on the filtered image and the gradient in y direction, and then we perform the outer product like gxs, gxy, and gy. So this one, gxs, gxy, gxy, and gy. So we are performing the same steps that we were discussing so far. So once we get these three images, these three gradient maps, we create a window of 13 by 13 similar to this. So we create a window here, this window here, which is 13 by 13, and we apply this window to all of the gradients like gxs, gxy, and gy because they are convolved in the computation. The window is convolved with the computation, and we consider them as A matrix, A11, A12, and A22. So if you can recall here, this is the A matrix, right? We refer to this matrix as A. So in A, the values are multiplied with xi, the values are convolved with xy, and this side. So once we have the images A11, A12, and A22, we have a kind of a 2 by 2 matrix here, like this. So we create a 2 by 2 matrix, and then what we will do is we will compute the harmonic mean. So this is the harmonic mean. So what we want to compare is the region from the harmonic A to the base A. So first we compute the determinant, and then we compute the trace, and then we apply the harmonic mean to get the interest score. Now while we get the interest score, there will be some computations where the MATLAB will return the value n, a, n, not a number. So when we will perform further operations, this NAM will create some problems. So basically what we are going to do with this command is that we will search the index values where the values are actually NAN, and we replace them with zeros. So there is no problem in the computation. So let's just run this code and let's see what happens. So let's just save this code as SSD. So this is the original image. This is the original image, and this is a kind of filtered image, the blur image which we have created through the standard deviation. and then we compute this x direction and y direction gradient here, so they can be represented here. This is the x direction and this is the y direction. So let's just look at the variables here. So if we look at the variables, we will see that we have this scores here. This is the score. And when we see the score image, we see these white patches. So we say that these actually patches are the stable ones. And if we consider these patches to match, then we have a good chance of matching and we have a good chance of tracking the points easily. So point and patch features is that we want to find a distinctive point or patches in the image which could match these features to 3D model or object recognition or for tracking or motion estimation. So we want the patches that are locally unique. We have already discussed that what kinds of features are locally unique and what kind of features are distinctive. So good types of features may be bright dots or corners. Bad types of features will regions with constant value or long stay regions like this. So we'll look at the Moravec interest operator today and we'll see that how it works and what are the limitations to the Moravec, specifically the Moravec interest operator. We'll discuss the SIF in detail in our upcoming lectures. And I'll also show you one of the examples that how the KLP corner detector is different from Harris, what operation makes it different. So we'll just shed some light or we'll just have a discussion on an abstract matter for KLP corners. But let's discuss the Moravec interest operator. So Moravec interest operator is kind of works like this. So we have to find the points where the local variance in vertical, horizontal, and diagonal directions are all high. So we perform the variances in this horizontal direction, vertical direction, and the diagonal directions. And this is a kind of a computation which we perform. Like V1 is the variance, and V2 is the variance. And what we will do is we compute the interest value by taking out the minimum from all of these variables. Now the example is that Moravec interest operator. If in uniform regions, if you consider this like the moving from horizontal direction and the moving from vertical direction, so we have only 0 and 1, so our mean would be 0.5, right? So if we move in the horizontal direction, so what we can calculate is mean 1 upon n summation of xi minus mu square. That's the formula for the variance. So if you compute it, this will be 1 upon n and n by 2, which is minus 0.5 whole square because this is the mean. So it's minus 0.5 and positive 0.5. So n and n gets cancelled and this becomes 0.25. If you compute the total of this computation, you will see that the result is 0.25. But when you will perform it in the vertical direction, the variance results in 0. And if you perform the minimum of the vertical and horizontal, you will receive the 0. And 0 refers to nothing else. There is no variance. So what we want to do is we want to find some of the variance. And this is one of the problems with Moravec. Now, considering this, if you have a certain kind of corner, not the edge in only one direction, you will get the variance in all the directions and then it will be easy to compute the minimum and easy to get the value for each of the variance. So that's the advantage which we get when we consider the corner points rather than each. So this is one of the example of monolithic interest points with window size 15 and threshold is 100 and local maxima between 15 pixels. So see how many responses we are getting and what responses actually we are getting. So see, this is a kind of a edge in this direction and a single direction. This let me show you this. So this occurs when you do not have zero pattern. So basically, I'll show you that how to eliminate this in the coding example. But we have to like remove these points because this is a kind of a homogeneous region, but because they are image corners, they are kind of considered as the interest points. So, with the notes of implementation, recall that the definition of variance and its alternative formulation is this. This is the formulation for variance. Again, it's like the same A minus B whole square formula, which can be extended as A square minus 2AB plus B square. So if we expand this, this is of course A and this is B, so this will be xi square minus 2 mu xi plus mu square. Now let's write it in a separate form. So this is 1 upon n, let's decompose it. This is 1 upon n I 1 to n xi square, and this is the as previously I recall that if we do not have this ith term, we can take out those terms out of the summation. So this 2 and mu does not have an I term, so we can take out this 2 mu out of the summation. So this will be 2 mu divided by this n and summation of xi values. And then again, this mu I has nothing to do with the summation, so this mu square will be taken out of the summation divided by n, and what will remain inside the summation is 1. So I want to I want to focus here. So if the summation of 1 is I 1, so it's like 1 will be added n times. So this is n. So if 1 is added n times, it will result in n. Let's say if you add 1 10 times, what you get is 1 multiplied by 10. So it's the same, right? So applying the same concept here, that if 1 is added 10 times, so you can just multiply it with the n and you will get n. So you will get here mu square upon n multiplied by n. And n and n gets cancelled out here. This gets cancelled out and you will get mu square. Similarly, what is the formulation for mean? The mean is actually the summation of xi values divided by total number of points. Now this is mean, right? What we can do from here is that we consider this part and we can replace it with mean. So this will be 2 mu dot mean, and this will result in 2 mu square, and this will be the same. Now here, this is 2 mu square and this is mu square, so 1 of the mu square gets cancelled out and we will get only mu square. So this is what we get. 1 upon n I equals to 1 to n xi square minus mu square. So rather than running the numerous nested for loops here, because this will require a nested for loop in MATLAB, what we can do is we can compute the mean of local window at each point on this, and we can compute the square at each point in local sum and combine to get the variance. So to compute the local mean at each point, we can compute the square at each point and local sum, and we can calculate the difference to get the local weight. So this is a kind of an implementation which does not require nested for loops, and it's kind of a vectorized implementation, so it's quite fast. So what we can do is we can first create the horizontal this one. So remember in Autodesk, what we do is we create a single vector, like three horizontal variants in vertical direction, variants in horizontal direction. So this is a kind of vectors. So this is one vector, this is one vector, this is one vector, this is one vector. So these are all vectors. So let's say we create a vector which is message of once, and then we apply this filter. So it's like 1 upon n multiplied by n filter alpha message mean of horizontal. And for this square root, there's no more this formula, right? We are just implementing this. We are just implementing the system. So I square is I squared with all the elements. So this dot sign is element wise operation. For U to H, what we do is we again apply the mean on the filtered image of the square root, and then we get the variance from U to H minus the mean. So it's like this. So this is U to H and this is U. Yes. Now, if you this is a graphical representation that if you apply this vector to the image, you will get UH because you are applying this filter to this and you will get UH. Of course, you can get the squared values by just squaring it, and then again applying this filter to this squared values, we will get this U2H, and once we get this, we can just use these two and subtract them to get this way. And once we calculate the variance in horizontal direction, of course, we can use this HH in vertical direction, we can use this HH in diagonal direction to create the variance in horizontal, variance in vertical, variance in diagonal 1, variance in diagonal 2, and then we calculate the minimum of all these variances and we get the interest point. So this is the kind of implementation. So let's say we have the same image we want to read, and we create a 15 by 15 window. So this is creating a horizontal vector, and transposing it will this is the vertical vector. Now I command is a kind of an identity matrix. So it creates an identity matrix of n by n. So identity matrix of 3 by 3 looks like this. 1, 0, 0, 0, 0, 0, 0. So this is a kind of identity matrix where the diagonal elements are 1 and all other things are 0. So this is the created relation of diagonal matrix where you will only get a diagonal response like this with the command IR. So this is the first diagonal filter and this is the second diagonal filter. So what we are doing is we are applying the filter in horizontal direction, vertical direction, diagonal direction 1 and diagonal direction 2. Remember, we are applying this operation. Now Then we will apply the squared values. And once we apply the squared values, we apply again the horizontal, vertical, and diagonal to the circle. Let's see this part and this part. And once we have this, we compute the variances in the horizontal, in the vertical, in the diagonal, and diagonal. Now, why we compute the minimum making this into separately is that these are the vectors and these are the matrices. So comparing the minimum will result in some error. So basically what we are going to do is first compute the minimum within the vectors and minimum within the matrices, and then we compute the single minimum. So what we get from this is this. See, this is the horizontal, this is the vertical, this is the diagonal, this is the diagonal. And if we calculate the minimum scores from this, we get this one. You see now we are getting unit interest points, which is the minimum in the whole direction. So this is these are the patches or these are the corner points which we can use and then interest point to get the matching or the. The problem with the monorack is it's so in this case if you consider this horizontal and vertical and diagonal, all they will respond is 0 because we will get the variance here as 0. And this is not a corner, this is a kind of a step edge but a uniform step edge. So when applying the monorack on these kind of images, it does not help in recognizing or in returning good text. So that's the problem with MRI, and that problem is actually solved with Harris-Corner detectors and PLC detectors because they consider not the minimum variance but kind of eigenvector implementation or eigenvalue implementation. So remember this demo previously where we did some kind of mapping that how we can get the interest points like this one. So let's just extend this analysis into the MATLAB code. So what we want to do is we want to find the local maximum of these points. Remember we found map. So simply finding all the points greater than the threshold will leave too many points like this. See, we get this binary map when we threshold. So what we should do is we find a greater threshold. We should find the points which are greater than the threshold and which have a local maximum. So how we can consider the local maximum? Let's say if the peaks are smooth here, and you can test each point to see if it is higher than its neighbor. So this point is higher than its neighbors. Similarly, this point is higher than this, or this point is higher than this, and this point is higher than its neighbors. Let's just consider these. So in one dimensional, these points are higher than its neighbors, and if we use these thresholds, we get only one single point. But we are not dealing with one dimensional, we are dealing with two dimensional because images are represented in matrices. So what we have to do is we have to look in the neighbors, like x neighbor and y neighbor and so on. So the MATLAB code for this is just this kind of implementation to find the maximum response in the neighborhood. Now the problem with this is that if you have smooth peaks, then you have too many vector features. So it's like instead if we find the local maximum within the range of 2 and 2, like this should be greater than this and this should be greater than this. These so That's where we can get unique responses. But the problem is that if this is smooth, like if you have a smoother version of this is better than this is again yielding the same response. This is response. So the local maximum within plus minus 2 is a kind of smooth behavior. So instead, finding points that are local regional maxima, what we can do is we can find the largest point within a region. So we use a kind of a window, a kind of a threshold. And we can do it by calculating the largest value within the distance n. And it refers to the dilation process. And this is the command which we can apply in MATLAB to perform this kind of dilation operation. So what it does is find those points that are equal to the local maximum. Now let's see one of the examples. So if you have a scope array S like this, you get a lot of points like this. And these are many feature responses which we do not want. So what we can do is we can dilate the scope array with the sliding window of 15 and see how many points we have reduced. So this is what we want. This is what we are looking for. Minimum responses. So this is a kind of a MATLAB implementation for this. So we select a radius which is n for non-maximum suppression. So we find the local maxima with this command. So we have already showed you that this command is going to be used for dilation of suppression. So we are applying this operation here. Note that we do not want to detect points that are too close to the border. Remember this problem which I already explained you that we do not want to detect these points that are close to the border. So for avoiding this kind of problem, we can use this. So if the points are near to border, we zero them. So then we get a list of the indices of the potential interest points, the response is the maximum, and then we get the values of those maximum response. And look what happens here. Let's see what happens here. So we have these gradient maps here, as we had before. And let's see the interest points. You see here, there are some maximum responses which we discussed earlier in the slides. And these are the values. So now see we have only 18 responses. So these are the 18 responses we have got from the images rather than many responses. So let's identify those interest points. Once you have the scores, you can decide which points to identify as interest points. And you could choose the points with the top n score. So you can just arrange them in a descending order. So the highest score should be at the top and the lowest score should be at the bottom. And you can just choose some of the top scores. So we can run this code snippet, which is a kind of draws a box around the scores which we have. If we run this code, this is a kind like we use this values which we have found, and we select the values which are greater than threshold, and we locate those values and then draw a kind of box. So let's see what it does. So we just pasted the code here, which we discussed in the last slide. and it draws the rectangle on. So we have to first specify the threshold. The threshold here will specify the kind of a code option. So you can play around with the threshold because it's a hyperparameter, so you have to optimize it or to try different values. Now see, these are the interest points which have been detected by our method, the sum of square differences. So these are the potential patches which can be used to kind of match or track the object. So matching interest point is with respect to this expression. We have already discussed this expression previously, but we discussed it with respect to the same image. Now we want to apply it to a different image. Now we want to compare two images. Now previously we were interested in these terms. Previously we were interested in these terms, and they are a kind of an autocorrelation. So autocorrelation means that this this time will be solely focused on I1 image, will be the translated image, and therefore will be solely focused on the reference image. But what we are interested is the cross correlation. So this time is actually representing the cross correlation, which is taking into account both the image. So the middle term is the cross correlation of I1 and I0. It is high when AI1 matches I0, and it is low when it does not match it. So under certain conditions, minimizing the SFP is equivalent to maximizing the cross correlation. And that's what we want when it is performed efficiently in the frequency domain, because it's then when we do not have to perform convolution operation, rather than we can just perform the multiplication operation. So correlation is a sum of products of corresponding terms, and it can be written like this. So it's kind of a convolutional operation, sliding either from left to right or to bottom and adding all the intensity values within those windows. So we can represent it in this way. But we can think of correlation as a dot product of vectors W and F. So it's a kind of a W1F1, W2F2, W3F3, and so forth within M by N range. And it can also be written rotationally on the platform. So if the images W and F are similar, their vectors in m dimensional space are aligned. So in this case, if we write it like the absolute value of W, absolute value of F, and cos theta. Now cos theta is the angle between W and F. If they are perfectly aligned, the theta value will be 0, and if there is some difference, then there will be kind of theta. So correlation can do matching, and if you have a certain kind of a template like this, so this is a template, and it moves from left to right up to bottom in the sliding rotation. So it tries to find an instance of W in image of XY, right? It tries to find this patch in this blue image. So the correlation score is computed at each point where the window slides, and the computation of the scores are done in this manner. Now this is a kind of a padding, because as I told, as we discussed in our previous lectures, that if you have this kind of window, this window, the central point, should have to be aligned with the first element. So in that case, if you center align your point, then the window looks like this. So these elements go out of the range. So we have to pad, we have to apply a zero pad. So for the template matching, since F is not constant everywhere, we need to normalize, and it's also good because sometimes you have noise. So for eliminating the noise, and for dealing with this F is not constant everywhere, we can get better precision by subtracting off the means. So if you subtract out the means here, it means that you are actually like maintaining the consistency within the image. So you are actually normalizing the image. So that's why we call them normalized cross correlation coefficient. And you can apply this formula and you can just subtract the mean of the window and the mean of the image from these, and again you have to subtract the mean of window and mean of the image from the norm values as well in the region. So if you get the plus 1 score, it means that it is a perfect match, and if you get a minus 1 score, it means that it is a perfectly opposite match, so it does not match. So that's what we can use for matching. And basically, there is a built-in command in MATLAB for this normalized cross correlation, so you do not have to write this whole equation to compute the cross correlation at each point of the sliding window, so you can just use this command norm x or so this is the normalized cross correlation command built-in command. So let's see one of the examples. So we have to track a point from one image to the next, and we want to look for this patch. So we will use the built-in command improp to get this template, and then we'll use normalized cross command for matching this template onto this image. So next is the command. So let's just read the image. So once we read the image, so once we read the image, we can show the image here. So this is the image. And now we'll use the crop command, crop command, to select the particular text which we want to match in the image. So let's just select this one and we copy the position of that image. You can also copy the position and you can apply the bounding box to it to segment it. So this is the crop image which we got. This is 17 by 22 size. And let's read another image which is the translated version of the translation shift to the original image. Let's see the image first. So it's better to differentiate, or it's better to show these images side by side. So now what I'll do is I'll create another window to show you both the images, to show you that there is a translational shift in both the images. You can see this is the original image and this is the translation shift image as we discussed in last class. So now we'll apply this normx for command, which is the built-in command for normalized cross correlation. We will provide the template which we have cropped from first image, and then we will find that particular crop patch on the next image, and we'll calculate the scores for it. So once you calculate the scores for it, you can visualize the scores. So higher the scores, it will be represented as brighter spots. So the brighter spots are the higher scores. So you can see that this particular spot is quite brighter, so it has the highest score among all of the scores. Now, handling more general viewpoints cannot be performed through template matching. So cross correlation assumes only translation. Where if you apply the translation, then of course the cross correlation can be applied for matching. But if the viewpoint changes, like if there is a rotation or if there is a scaling operation performed, then the cross-correlation would not yield better results. So we need features that are invariant to translation, rotation, scale, and viewpoint. So in the next lectures, we will mostly talk about those features which are invariant to translation, rotation, and scale, especially the SIF, like the scale invariant feature. The TLP tracker is a kind of a interest point detector, the same as of corners, but there is one thing which we perform here is, let me write it for you. There is an affine transformation. So we perform affine transformation. We have already discussed about affine transformation in our previous lectures, if you can remember. So affine transformation is a kind of rotation and translation combined. So here we have one, one, two, 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 this is translation, this is translation. So this is a kind of a translation, affine transformation matrix. So this is R, E, communication matrix and translation command. So once you perform this on these kind of patches, the first row shows you that there is a difference in the viewpoint. This time shows there is a difference in the viewpoint, but when you apply affine transformation, so it kind of performs a warp effect, and you will see that it's now more of a consistent when you see the patches, and the patches are now easy to locate and easy to fill. So basically, if you apply the affine transformation prior, then you can say that we are using a 28 data, which was actually proposed by Shimon International before. So if you want to read more about it, you can refer to this paper, which we just looked at, which was published in Computer Vision and Practical Computation Conference, which is a kind of a flagship conference in computer vision field since many years. So this was published in 1992, and you can look for more details about this paper if you are interested in it. Now let's see one of the examples in Python, that how you can like detect the corners in Python. So if you have the OpenCV package installed in Python, as discussed in our earlier lectures, so what you have to just do is you have to import the OpenCV package and the numpy, and you have to read the image first. So once you read the image, what you can do is you can just convert it into grayscale image. And after you convert it to grayscale image, this is the built-in command in OpenCV, which is that is corner detector for corner virus. And you can apply this command to detect the corners. So if the results are validated, you can use this command to perform the validate operation as we did in MATLAB, and you can apply a threshold to eliminate the what you say is false responses, and then you can see that there is an image to false responses. Or reduce false responses. So this is a kind of a code which can be implemented in Python for corner detection. I hope you got the point that why we use corners and what are the importance of corners, why they are important for applications such as motion tracking, and how we can select the patches which can provide us better results for matching and which can provide us better results for tracking, and what is the stability criteria and how we conclude some of the squad differences. I hope that you have understood the application of Moravec problem and how to detect them. And I hope that you have some know-how and how we can implement this kind of stuff in MATLAB and Python. So if you have any questions, please prepare your questions with respect to the slide numbers. So we'll have a live Q&A session, and you can ask all those questions in that particular session, and I'll try to answer all your queries. And also, if you have trouble in difficulty in understanding the mode of language I am using, so please refer to the slide number and I'll try to explain in the native language that what are the concepts, what are the key concepts in that slide, or what are the key concepts related to that particular mode. So hope you have understood or you have grasped the concepts in this video lecture, and we'll meet in the Q&A sessions shortly, and hope that you will stay safe and healthy in this kind of situation. Thank you.